So, next speaker, Claudia Cuttano. She works as a research scientist intern at Adobe. She's a true computer vision goat. She has a PhD in computer vision. She has a lot of papers in the field. And she's going to talk about how new capabilities are emerging from visual foundation models. So let's welcome her with a round of applause.
So, hello everyone. My name is Claudia Cuttano. I am a PhD student at Politecnico di Torino in collaboration with TU Darmstadt in Germany, where I spent the last year. Right now, I'm an intern at Adobe in France, but I'm very close to finish. And in a few weeks, I will start an internship at Meta in New York. So in this half an hour, I would like to talk about the usage of visual foundation models for dense pixel-level tasks in computer vision. So I'm pretty sure that all of you know what is computer vision, but just to be sure. So when we talk about computer vision, we are referring to all the tasks that involve visual understanding from images and videos. So we have tasks like semantic segmentation, where we want to classify each pixel of an image. We have tasks such as depth estimation, where we want to estimate the depth of a scene. And we have tasks such as object detection, where we want to estimate bounding boxes for the objects. So in the current landscape of computer vision, we have two strong foundation models that are segment anything and Dino. So segment anything is a foundation model from Meta that was released in 2023. This is a foundation model for promptable image segmentation that was trained on a lot of data, in particular more than 1 billion images paired with segmentation masks. So we can do promptable image segmentation. This means that we have an image. The user can provide a geometric prompt, for example, a point that is just a click on the object or a bounding box, and the model will automatically produce a segmentation mask for the object. Then in 2024, Meta released a follow-up. This is Segment Anything 2, which is basically extending the capabilities of Segment Anything 1 from images to video. So we can use this model, this time also on video. So we have this video, the user provides a geometric prompt, a click on an object, and the model again will produce a segmentation mask for, in this case, the penguin, but will also track this object across frames in the video. And then, more recently, Meta released a new model, this is Segment Anything 3. It has the same capabilities of Segment Anything 1 and Segment Anything 2, but this time we can also prompt the model with a class label. For example, in this case, we have the same video. We can type the word penguin. The model will understand the prompt that we are providing, will recognize all the penguins in the image, will segment all the penguins, and will also track these penguins frame by frame. So this model is a very powerful tool for a lot of downstream applications, such as data annotation. So, the foundation model that probably had the biggest impact is actually Dino. That is also a foundation model from Meta that was released in 2023. So this is based on a very different principle, that is the principle of self-supervision. So Segment Anything was trained on a lot of data, but still annotated data for segmentation. So the model has seen a lot of images paired with segmentation masks. So Dino v2 instead is trained on images without any label. And so the point is that with self-supervision, we can scale up the training process because we can train on more data. But the point of self-supervision is that the effect is that the model implicitly learns more semantically meaningful visual representations that we can use for a lot of downstream tasks with zero to minimal adaptation. And so Dino v2 is basically the backbone for all the modern computer vision pipelines. We also have a new model, Dino v3, a very recent model. This is essentially Dino v2 trained with more data and with a new objective that improves the representation quality. So with Segment Anything, we have a model with the capability to produce class-agnostic segmentation masks. Class-agnostic means that the model is producing a segmentation mask for the penguin, but is not telling us that this is a penguin. And with Dino, instead, we have a model that trained with self-supervision produce semantically rich representation. So our question is, how can we exploit these representations for dense pixel-level tasks? So imagine that we have a video and we have a complex textual query, for example, the cat that is playing with the feather toy. So we would like to have a model that is able to reason on this query, understand which is the object that we want to segment, and then segment the object and track it. But also we would like to have a model where we can provide a visual example of what we want to segment. We provide a visual example of a boat, and the model is able to understand that we want to segment other boats in our, for example, database. And also we would like to have a model that can be prompt with visual examples from very different domains, such as medical, underwater, or aerial data, at different granularities, so not only object level, but also part level, where we target only a part of the object. And finally, we would like to have a model that we can prompt with key points that are more fine-grained semantic concepts. So the common approach nowadays is to enable this task by taking segment anything and Dino, putting them all together, or instead taking segment anything or Dino and coupling this model with an external visual language model, or we can take one of the two models and entirely fine-tune it. So in the past 2 years, we challenged this common belief, showing that in these foundation models, we have enough information that we can use to solve these dense pixel-level tasks without having to pair multiple foundation models in order to have models that are able to better generalize and that are more efficient because we just built on a single model. So let's start from the semantic understanding of segment anything. We have our video, we have our textual query. So the task that we are solving is the task of referring video object segmentation. So the common approach is to take a visual language model. We have the video, we have the textual query, we feed this input into the model produces a bounding box for the object that we are targeting, and then we just give this box to segment anything that will produce the segmentation mask. So our question is, can we enable text-driven video segmentation without using expensive external visual language models, empowering directly the representation of segment anything? So we propose this model that is SemWise, where we make segment anything to wiser by enabling text understanding, temporal modeling, and the capability to correct tracking mistakes without any fine-tuning of the original model and without relying on external visual language models. So I want to show you an example to highlight the challenging of the task and how SemWise solves them. So here there is a clip from The Lord of the Rings. So we have the textual query, the guy who is drinking, and we want to process the video in a streaming fashion. So we don't have the full video in advance. So at the beginning, it's not clear who is the correct person to track because nobody of the two people is actually performing the action of drinking. However, one of the two persons is holding the glass more visibly, so SemWise starts tracking this person. But then the other person actually starts drinking. So thanks to our learnable correction, we are able to switch to the correct person, and we keep tracking this person as the action unfolds. We are able to handle occlusion, so when the target object is no longer present in the video, and then to recover the object when it reappears, thanks to the memory bank mechanism. So I don't want to go too deep into the technical details, but the point is that we are using segment anything 2. So this is what you can see in the blue part. So this is the segment anything 2 model that is entirely frozen. Then we add a very lightweight text encoder, so not an LLM, just a text encoder that is pretty lightweight. And we also keep this text encoder frozen. And the idea is to only add and train few dedicated modules to enable the visual textual understanding. And the point is that we are able to enable the task by adding and training less than 5 million trainable parameters. So if I have to sum up SemWise in 3 points, I would like to say that SemWise does not delegate the visual textual alignment to external visual language models. And so this means that we have a model that is more efficient because we are not using external encoders. We do not fine-tune segment anything 2. So we only add less than 5 trainable million parameters. And then finally, we do not disrupt the capability of Segment Anything 2 to work in a streaming fashion. So this means that we don't have to obtain the full video in advance. But more broadly, the fact that we were able to align the textual and visual modalities so easily with just less than 5 million parameters means that there is some semantic structure in the encoder. So we use this as a starting point for our second work. What we were saying at the beginning is that we have our model and we would like to prompt the model with a visual example. So we have our data set, this is pretty big, we don't want to segment all the boats in all the images, so what we would like to do is to only segment a simple example, and then we want to provide the model with this example. The model should understand the concept that we want to segment. So this is a task of few-shot segmentation. So the idea is that to solve this problem, we have to solve two coupled problems. First, we need to establish semantic correspondences between the reference concept and the target image to localize the concept that we want to segment. And then we need to produce a spatially coherent segmentation mask. So Vision Foundation models provide a strong starting point. As we were saying, we have DynoV2 that has strong semantic features that we can use to establish correspondences. And we have Segment Anything that produce high-quality class-agnostic segmentation masks. So prior work have built on this capability in two main directions. Some of them use a single foundation model, such as Dyno, and fine-tune it for segmentation, training a segmentation decoder on top of Dyno to recover the missing segmentation capabilities. Others remain training-free, but they compose multiple frozen foundation models that are DynoV2 for correspondences and Segment Anything for segmentation. So our question is, we have Segment Anything 2. Of course, we can segment with Segment Anything 2, and we also believe that there is a semantic structure in the model that we can use. So we started with a very simple experiment. So we take images from the medical domain, where we have very low semantic variability and high visual similarity. So for example, images from the medical domain where we have lungs, so you can see that the lungs are pretty similar to each other, and we provide SEM2 with the first example of the lung, and we task the model to propagate this mask, so we pretend these images to be part of a video. And what we actually found is that Segment Anything 2 outperforms prior state-of-the-art approaches that are even fine-tuned for this specific task. But then we repeat the same experiment on another dataset that is Coco, where we have high semantic shift. So we have both, but of course the representation of a boat could be very different. So we task the model to do again the same mask propagation of a boat, and what we actually found is that the model is completely failing. So the natural conclusion would be that Segment Anything 2, being designed to do tracking, does not really understand object semantics, but just the instance level appearance. But we challenge this interpretation and we ask, what if the semantic structure is actually there, just mixed with other signals? And so we did a simple experiment. We take the architecture of Segment Anything 2, entirely frozen, and we just focus on the image encoder. And what we did was put a linear layer on top of this frozen representation, and we tried to train this linear layer for a high semantics task that is semantic segmentation. So we want to see if we are able to predict segmentation masks for an image given a frozen image encoder and just a linear layer. And what we actually found is that the frozen Segment Anything 2 features plus a simple linear projection provide strong semantic performance. And so this means that the semantic information is actually present in the Segment Anything 2 features. It just not is explicitly exposed, but can be revealed by a simple projection. So the method is super simple. We take Segment Anything 2 and we just train an adaptation layer inside the image encoder. And so at the end, we obtain Sansa, that is a semantically aligned Segment Anything model, and we can use this model for few-shot segmentation. So in few-shot segmentation, we are training on a base set of classes, and then we are testing the model on new classes never seen during training. For example, here we are given the example of a dog to the model, and then we ask the model to segment all the dogs, even when we have very high domain and style shift. And as you can see, this is working pretty well with multiple classes. So we also maintain the promptability of the segment anything model. Given that we are not fine-tuning at all the model, we can provide the model with cheaper prompts. So we don't really want to annotate each pixel of an image for our example. So we can just provide a point, we can provide a box, and we can even provide a scribble, so a simple line on the object that we want to segment. So again, 3 highlights. This is the first solution to fully leverage segment anything 2 for few-shot segmentation without using external feature encoders such as Dino. We do not fine-tune any of the weights of the segment anything architecture. And finally, we have a model that is 3 to 5 times faster than the previous solutions. But what we actually found is that given that we are fine-tuning the model, then SANSA provides poor generalization if we test this model on very different domains, such as medical, underwater, or aerial data. And this is something that we cannot avoid because we have to train our linear projection in order to make this semantic structure explicit. And so we really cared about generalization, and so during the last year, we focused on this problem with a model that we just presented at CVPR last week. So in context segmentation, we again have a single annotated example that defines the visual concept that we want to segment. But now the images may come from very different domains, such as medical, underwater, or aerial data. And the concept may also be defined at different granularities. So at object level, of course, but also at part level, where we target only a part of the object, or even at personalized level, where we target the same physical instance of the object. So in-context segmentation aims to solve this broad set of segmentation tasks by learning or designing a single unified model that can infer what to segment from the provided in-context example without having to retrain for each dataset, domain, or granularity. And in this paper, what we show is that in-context segmentation emerges from the frozen self-supervised features of the recently released Dino v3 foundation model, without having to train a segmentation decoder, without having to fine-tune for the task, and without composing multiple foundation models. So if we look again at this slide, here we have the prior works. What we do is to test this model on generalization. So we can see performance across different domains and granularities, and we see that there is a clear trade-off. So task-specific fine-tuning method maintain the efficiency of a single encoder design. They excel in domain, so where you can see the marker on the data that they have seen during training, but they really degrade out of distribution. Training-free pipelines instead generalize better, but they rely on large multi-stage architectures. And so we show that the dense semantically strong features of Dino v3 can unlock directly this task without fine-tuning and without using an external mask generator such as segment anything. So to answer this question, what we did was to look inside the Dino v3 feature space. So what we found is that the dense representation of Dino v3 are all you need for segmentation. So in particular, what we did was to simply take these frozen features and apply a very simple and old agglomerative algorithm that is the agglomerative clustering, sorry. And what we found is that this representation induces a structured decomposition of the scene without any training, without a segmentation decoder. So we obtain some clusters and so some masks that are very similar to the ones that you would obtain with segment anything that was specifically trained for segmentation. So we were super happy. We have our segmentation directly from the representation without training, but actually what we found is something that was unexpected. So when we are computing similarities across images, what we observe is that Dino v3 has a strong positional related signal that we denote as positional bias. So we take two images, and what we do is to select a patch on the bird tail on the reference image. And then we compute the similarity between this patch and all the target patches, and we visualize this activation map. What you can see is that we have the correct semantic match on the bird tail. This is what we would expect. But the model is also activating on the left side of the image just because it reflects the absolute coordinate of the reference patch in the reference image. And so this effect is systematic and is more pronounced on regions with low semantic content, such as background or low texture areas. So in this paper, we propose a very simple training-free debiasing strategy which removes this positional component, improving the quality of these representations. So at the end of this process, maybe we can skip it. So at the end of this process, we obtain two complementary feature spaces. We have the original features that we can use to do clustering, so to obtain our segmentation masks. And then we have our debias features that we can use to have reliable semantic matches. So the method is actually very simple. Given an image, we apply agglomerative clustering, we obtain a set of candidate clusters, and then we use our debias features to localize the relevant clusters to produce the final mask. So if we look again at the performance, what we found is that inside consistently outperforms all the prior approaches, so the ones that are based on Dino v2 plus segment anything, and it also provides better generalization compared to task-specific fine-tuning method. So inside is the best trade-off, as it maintains the efficiency of a single encoder design while also preserving the generalization of the training-free solutions. So again, 3 highlights. This solution is completely training-free. This works across a lot of domains and different granularities, and we also offers a look inside the Dino v3 feature space. We show that the dense representation of Dino v3 are particularly useful for segmentation, and we also discover a positional bias in the Dino v3 features. And then finally, we ask, what if this semantic concept is defined not at the mask level, but at the point level, so at the level of a key point? So this is the task of semantic correspondence, where we want to estimate pixel-level correspondences between semantically equivalent object parts. So this is a fundamental primitive for a lot of applications. So for example, image editing, here on the left, and texture transfer, here on the right. And actually, this is a paper that started with a failed experiment. So what we were seeing is that the current approaches are basically taking Dino v2, and they are pairing this encoder with a generative model that is stable diffusion, so they have pretty complex pipeline to solve this task. So what we did was to simply take Dino v2 and then fine-tune this encoder on the sparse key points that we typically have in our benchmarks. And what we found is that our model was beating all the prior approaches on all the benchmarks, so we were super happy. But then what we did was to take new images with new key points that the model had never seen during training. So for example, you train a model where the key points on the cat are on the eyes and on the nose, and then you prompt the model with a key point on the paw of the cat. And what we actually saw is that the model was completely failing, so the performance were even lower than the frozen model. So here you can see what we actually found. So we have a metric that is the percentage of correct key points, and our model is the purple one. So on the left, you can see the performance in domain in overall localization. So are we actually finding the correct part where we expect the key point to be? And you can see that we were outperforming prior approaches. And in terms of pixel level precision, so the really exact key point at the pixel level, we were outperforming prior approaches a lot, so we have gains up to 10 points. And so this is the point. We have a seen key point, for example, a key point on the left ear of the cat. Our model is correctly predicting the point, while the original model was not. But then if we take another key point, for example, a key point on the belly, so you can see that our model is no longer able to predict the correct point, while the Dino v2 model, so the original model, was pretty good. And so what we saw is a consistent drop of the performance on these new challenging key points. And this is pretty critical, because in real world scenario, you don't really know which are the key points that you want to prompt. So our idea, I don't want to go into the technical details of that, but is that Dino v2 already has a very good representation. So maybe it's not perfect, but we have already a good representation in the feature space. So instead of discarding this structure at training time in order to train only on sparse key points, we use this as a source of self-supervision. So we try to use this structure to actually improve the training signal. And so this is the idea. We have our two objects. We have the manually annotated key points. We mine reliable matches. So these are points that are forward-backward consistent, so points that we can trust. Then we apply an algorithm that is the Delaunay triangulation in order to densify and draw triangles to connect all these points across the object surface. And finally, we warp each triangle from the source to the target. So at the end of this process, we have a set of dense correspondences across the entire object, and we can use these pseudo-labels at training time to improve the training signal. So at the end, you can see we have the features of the frozen Dino-V2 model. They were already good. After sparse fine-tuning, we have that the features are contracting across on the supervised key points, for example, on the eyes of the dog. And then finally, you can see that our features not only preserve the quality of the original model, but actually improve them. So we have some tables. What we found is that our model is outperforming all the prior approaches in domain and out of domain. So 3 highlights, this model, so what we are delivering is a model that is more accurate than the prior solutions. It provides better generalization to unseen key points and unseen categories, while being 10 times faster than the prior approaches. So to conclude, in this line of research, what we did is to look inside the Vision Foundation models. And we try to understand what is already inside these representations and how we can use them for dense pixel-level tasks. So the idea is to follow a simple direction, going against the standard trend of composing multiple models together in order to have complex and inefficient pipeline. But more broadly, I think that this line of research points toward real-world generalization. So I feel like sometimes, especially in academia, we are focusing too much on hitting a new score on a benchmark and just put a new line on a table. But actually, I think that we should focus on designing unified models that remains general, efficient, and that we can also adapt to new tasks with no task-specific tuning. Thank you.
Thank you so much. Really, really interesting talk. So, do we have some questions? Okay. Don't be shy, by the way.
Thank you very much for the talk. You mentioned domain generalization. I'm curious to know whether or not you think it would generalize to vector-style graphics. So, for instance, like industrial blueprints, drawings, documents, architectural plans, and things like this. Like, do you think that this could apply, or it's a totally different set of methods and models that would be relevant?
So thank you. So I don't have a definite answer for this, of course, but I think that, so we are building on foundation models that they really have a strong understanding of the visual world. Like Dino-V2 has been trained on a lot of data that was taken from the internet. So I would say that it has enough knowledge to generalize to very extreme domains. Of course, we will have probably worse performance compared to natural images, but I would say that this is still something that should work.
Okay, do we have more questions, guys? Piotr?
So I noticed that you don't like those multi-model combos. So I want you to play the advocate of the devil and say to me, where did you notice that this approach fails? One thing that comes to my mind is advanced text prompts, where those models can, you said, oh, you can say it's on top of something or it's holding something. But in my experience, those models like Dino or Clip or Siglib, they fail when the prompt is more complex. But I'm curious about, have you noticed any other places where the combo could work, but those like unified approaches fail?
Yeah, so what I would say is that, of course, if we are increasing the complexity of a model, typically we can obtain better performance. But I also feel this is not always true. For example, in the task of few-shot segmentation, where you have a visual prompt, when you are constructing more complex pipelines, you have more point of failures. And if Dino is not able to provide the correct correspondence, then the model on top of that will automatically fail. So when we are trying to unifying things, we also have a single feature space, and sometimes this helps the model to actually, for example, ground the concept and then produce a coherent segmentation mask, because it really knows which is the concept and how it behaves in that feature space. And what I would also say is that so let's imagine that we take segment anything tree and we align the visual encoder with an LLM. Probably the performance will be great, but we are not at that point yet. And so what we actually do is to take models that are trained for different tasks, like you take grounding Dino that is working at image level, and then you want this model to reason over a complex textual query, so you can simply you cannot use this kind of model, but we are using that because we don't have anything better. And so I think that probably in the next years, we will have more unified solution, probably based on LLM. This is something that I still don't like a lot, but I know that it's something that we cannot avoid. And when we will be able to really align an LLM with a visual encoder and this will actually work, we will have performance that will be actually better than my works.
Okay, sorry, I do have a question for you. So since you work on this directly, I was wondering, is there any semantic where the few shot example in segmentation, so I just send a picture of both, and then I get all the segmentation for similar semantics. Like, is there any specific ones that actually fails a lot?
Yes, so of course the model is not working always. But so if I have to identify a problem, is the fact that when we are providing a model with a concept, there is a lot of ambiguity in the concept. So let's imagine that we are providing a concept of, I don't know, a Labrador, and then we have an image with other dogs. Do we really want to segment only the Labradors, or we want to segment all the dogs, or we want to segment all the animals? So there is an ambiguity in this task that cannot be really easily solved. And there are probably concepts that are not really working. I don't have a clear example right now, but yes, of course.
Okay. Guys, any question? There we go.
I really like the concept of having very generalizable models that are very adaptable. But I work closely with, more closely with Edge AI and TinyML, so my tool set is usually more limited due to compute capabilities. But I'm curious, do you think that this approach of more general models is also going to move towards Edge AI or in general TinyML, or is it something that is just going to stay where you have more computing capacity and this other field will remain with more task-specific models?
Yeah, I think that optimizing a generalizable model for Edge is very complex, because even if we take Dino, and so we have a teacher, we are distilling the model in smaller architectures, actually the knowledge that we can have in our biggest teacher is very hard, and you can see that it's reducing while we are going to more lightweight architecture. So I think that there is a trade-off that we have to consider. Right now, of course, if you have to do a specific task on Edge, I would just fine-tune the model for that task. I think that probably working on the distillation part and understand how to move the original knowledge into the final architecture is what would also enable better generalization when we are doing some sort of fine-tuning.
Okay, and you have a follow-up question as well. So since we just talked about how to put these models, that they are actually big. I think we were talking about almost close to 1 billion parameters, right? For the last one, no?
No, prior approaches has close to 1 billion parameters. So our model...
1 billion.
1 billion, okay. Yes. Our models are way more lightweight. So our models typically have 200 million parameters. So we have models that are actually small enough to be run on normal GPUs.
Okay, so is there like a set of approaches that you can actually or recommend to us if you want to take this model and put in production? Like for language model, like usually you have quantization, you have all the like Llama, CPP, all this set of tools that maybe for language models, because they are more, let's say, hype, you have more tools. So I was wondering, like, if you have to put this model in production today, so what would you actually do?
Yeah, so also here there is a trade-off. So I know that in LLM we actually have way bigger models. This is not really the case when we are talking about visual foundation models. So I know that everybody thinks that visual foundation models are actually big, but it's not really the case. Like for segment anything 2, we have the smallest version that is actually very small and is super fast. So I think that with visual foundation models, we already start from smaller models. And so I would again say understand how to distill them is probably the best solution and something that should actually work.
Thank you.
Nice talk. And I would like to ask you, basically the previous guy told us that segmentation model are not meant to be in production. What would you say to him? I don't know if it's here anymore, sorry. Guys, don't argue, please.
Yeah, of course, I don't really agree. So I mean, I have a bias, so I work in computer vision. I think that what we are doing is something that is useful. I think that also YOLO is actually useful. So I mean, the segment anything model, so now everyone loves the segment anything model, but segment anything is not something that is like a black box or something super strange. It's actually a transformer based on mass-to-former that is a standard architecture for segment anything that is not that different from YOLO. So I mean, computer vision for me is something that is still alive, and I think that, of course, we have VLM, but still the VLM are built on the vision encoder that we are doing in computer vision. So to me, computer vision is still something useful.
Who is right?
Yeah, I mean, I think that YOLO is also a very powerful model, and yeah, I'm joking.
Okay, so no more questions. Thank you so much. It was really, really a cool talk.